Professor Bodo Bookhagen, who is going to deliver a number of lectures on the quantitative geomorphology. Professor Bookhagen is currently professor in the University of Potsdam, Germany. He did his full diploma in computer science and geophysics. And after that, his diploma in geosciences from the Potsdam University, and it is followed by his PhD work from the Potsdam University. He worked on the Northwest Himalaya itself, and his work is one of the most cited work on the river terraces of the Himalayan rivers. And uh, and then after that, he joined University of Santa Barbara as a faculty. And after spending few years, then he moved to Potsdam University, and he's working on the number of aspects. So almost all the different disciplines of the quaternary geology. I mean, he's working on the digital data set, modeling, landscape evolution models, then chronology, CRN datings, and then climate analysis, paleoclimate. So all the things are there. And with his uh, wide spectrum of his work in the area of the quaternary geology, and you're mostly bringing the quantitative stuff in this round. I invite him to discuss things. Today, first thing, the focus will be on the DM data, and then later a few more new things will come. So, Bodo, thanks many.
No, thank you, Vikrant. Thank you, Vikrant. And it's always a pleasure to be here in Gandhinagar. So thank you. Thank you.
Good morning and hello, everyone. I'm very happy to be here, and I have been quite impressed with what you have been doing yesterday. I'm very familiar with Jérôme's work, and I'm certain that he has been keep you going on a couple of analytical things. I did enjoy the exercises that I've seen yesterday, and I actually spent some time last night on redoing some of the exercises that I would like to do with you today, just because I see that there are strong analytical skills available, and it will be good to exploit them. So what I would like to do in the first couple of minutes, give a short introduction of what I will be doing in the next 5 days, and then we zoom in on the topic of today's lecture. And the way I envision this to do is to do a mixture of lectures and lab exercises. So I do not intend to lecture for 2 hours and then leave the room and do something else. Instead, I'm planning to do this much more interactive. And that's why I'm hoping that everybody of you has a laptop with you. So after about 1 hour of lecture, we would dive into some of the Python digital elevation model analysis. So today is focused on digital elevation model analysis, and we will be discussing some processes and pitfalls and caveats using digital elevation models in describing hill slope processes, for example, or deriving river networks. And we will be doing this with synthetic and gridded data sets. So we will generate our own model, for example, of a Gaussian hill. So we will generate our own Gaussian two-dimensional function. We will take the analytical derivative of it, and we do the same in the gridded domain to see what effects happen when you grid things, how well you can describe slopes and curvatures, for example, and what are ways of calculating slope and curvature from a DEM. We will be working on Earth, Mars, and if we have time, maybe Moon, so that we look at some other planets to get an idea of slope distributions. If we have time, we get into kernel density functions to estimate two-dimensional histograms. I've seen someone give examples of this yesterday. Tomorrow is dedicated to landscape evolution modeling, so-called LAMPS, and I will be using LandLab to do that. I am not the programmer of LandLab, but I've been using it in the past. We will be working with our synthetic DEMs, for example, our Gaussian hill, but also a digital elevation model from the Baspa Valley up in the Himalayas to then run a forward landscape evolution model of what happens if the rivers continue to incise. And then we will add other processes such as landsliding, and we will not get into glacial erosion. That will be too much. We do fault scarp modeling exercises, so a simple linear offset of fault scarps, and we will look at how we can model landscapes that represent real world rivers, so using steepness indices. On Wednesday, I think it will be a good idea to spend some time on working with MATLAB, and just because this is the most widely used tool for analyzing topographic data, the so-called Topo Toolbox. Wolfgang Schwanghardt, he is the person who programmed it, is a person in Potsdam as well. And that will be MATLAB. In the next 2 days, we mostly focus on Python programming because we can do it here in our classroom. But there are some things that go incredibly easily with Topo Toolbox, so it will be good if you understand this and can use it. Thursday, we move on to a different topic. We will be talking about point clouds, and I will be talking about LiDAR and structure from motion point clouds. Structure from motion is a method that allows you to generate point clouds from overlapping imagery. This is what you usually do with drones when you collect high-resolution imagery. So we will be classifying point clouds, so separating vegetation and bare earth and ground, and we will be thinning and gridding point clouds. In other words, when we have a point cloud, how can we go from a point cloud to a gridded DEM for further analysis? Friday, the idea is to use a terrestrial LiDAR scanner from the Institute and generate our own point cloud of parts of the campus so that you get familiar with using the instrument and how this could be employed. Maybe if we have time, we get into some shape detection, how we can detect the pebbles on the ground, for example. We have been doing that 2 years ago in the Himalayas, where we collected lots of terrestrial LiDAR data from point bars to estimate the grain sizes. We have been doing that in the Central Andes as well. I can maybe give a short intro of this on Friday. Okay, so that's the roadmap. So this is what you have to expect in the next couple of days. The way it usually works is I like to keep it interactive. I keep on talking if I don't see a hand with a question. So when we do lab exercises, if you're stuck, if you have lost wherever we are, please just lift your hand and we will talk about it. I can't see what you have on your screens, and I'm not going to walk to the room and constantly check what you have on your screen. So if you're lost, please raise your hand, and then I know that we maybe repeat something. The other thing that I would like to mention is that I'm all about sharing the work and codes. And so last night I set up a GitHub repository, which is available here. It's called Quantitative Geomorphology IITGN. And all the lectures that I will be giving and all the codes, the Python codes and the MATLAB codes, the landscape evolution modeling, they will be available here. So I already put the DEM and the MATLAB Topo Toolbox and the LEM, the landscape evolution model, is on there too. On that GitHub page, I also have the schedule again. So what we are going to do in the next couple of days. Okay, that was a brief intro. In the next hour or so, I would like to talk to you about digital elevation models, how we can generate digital elevation models, and how we can derive slopes and aspects, for example, from digital elevation models, and then we dive into a Python exercise after the break. And I know, or actually I don't know your backgrounds, and I do understand that it's very, very diverse. So some of this intro class may be too easy for you. So bear with me. I'm trying to, cover all different levels of education, but I want to make sure that there are certain things that we all agree upon. And it may be a repetition for some of you, but it may actually be a good thing to hear this again. And I'm starting out with some applications of digital elevation models. And we will do this much more tomorrow and the next days, but I'm starting out with a very simple example of an application of a digital elevation model in an analog form. So not until about 1 or 2 decades ago, digital elevation models were not widely used, and you used the contour maps. And you could use contour maps to derive river networks, for example. And it's always good to be able to read maps and especially if you do field work, just because there exist great maps from the 60s and 70s that never have been digitized. So you don't have digital information of it. Nevertheless, those are extremely valuable maps because they often depict the terrain from a different decade. So they are great maps of glaciers in the Alps and in the Himalayas from several decades ago. And those can be used to estimate mass balance changes. So the first thing that I would like to ask you, which way does the water flow? And I will answer my own question at this point. And essentially there are ways to either look where the river is cutting the contour line, right? Clear, so you follow the steepest descent. But there's also the general rule that the name of the river is written in the flow direction so that you can follow the river. So as soon as you see the river name, you know in what direction the water is flowing. Going from this very simple first step, let's look at some other applications that have been used in the recent past, specifically during flooding. So the Hurricane Katrina in the US caused heavy flooding in New Orleans. And in order to understand in what direction the water is moving, you need to have very precise elevation information. And with those very precise elevation information, you can calculate the slope of the water and in what direction the water will be moving. This flooding prediction in New Orleans is nowadays, the flooding prediction in New Orleans is nowadays done through LiDAR data. So you have very precise elevation information that tells you what is the slope of the terrain and in what direction would the water be moving. Yeah, so you not only do that in New Orleans, you do that throughout Europe, and as far as I understand, there are some regions in India that have high resolution LiDAR data to predict flooding directions as well. So for those kind of very precise slope measurements that are required, you need a very precise digital elevation model. This would not be easily doable on an SOTM or on a Corsa digital elevation model. But zooming out again, zooming out to the entire continent of South America, another application of digital elevation models, for example, is to do flow routing on the digital elevation model. So follow the steepest descent, and then you can turn that flow accumulation into a river network. So these rivers that you see here, they are not taken from satellite images, they are taken from the flow direction and flow accumulation calculations. So I've just been using the elevation data, and I've been looking at the steepest descent in a 3x3 moving window, in what direction is the water flowing, and then I let the rivers accumulate, and they will pretty much follow the real rivers. Of course, this line here is scaled by the thickness. In the DEM world, this is only a single pixel, and it's of course not true that the Amazon River is only 30 or 90 meters wide. It is much wider, but in a modeling DEM world, you will flow route most of your water through a single line. You also note here the Central Andes, the internally drained part of the Central Andes. This is the second largest orogenic plateau after the Tibetan plateau, and essentially no water is leaving this region. Another application of DEMs is specifically used for glacial modeling and ecology modeling is calculating the solar radiation. So by knowing the aspect, essentially the direction the terrain is facing, and calculating the sun angle, because we have a latitude of that and the elevation, we can calculate the solar radiation or even the solar flux. And that tells us how much energy is being distributed on each of the hill slopes. That is very useful for ecological modeling, or if you want to calculate the energy balance of a glacier. Some of you, or I assume many of you, are familiar with the way that you use hill shading. So in other words, you can position the terrain at you can position the sun at a certain location that then generates the shadow of the terrain. And this is not only for visualization purpose, so not only for identifying where do I have the 3D relief. This is also used for identifying pixels that are shadowed, for example. So when you're doing cosmogenic radionuclides and you're interested in identifying what is the solar input at a certain angle on a surface, you can do that through Hill shading. So you would get an information of how much is exposed to the sky, how much of the terrain is being exposed to the sky. More modern DEMs also allow you to look at bathymetry, below water information. So this is a LiDAR DEM, and you see that the normal near-infrared LiDAR does not capture water very well, just because it cannot penetrate into water. It's being absorbed by water. But there you could use a green or a blue wavelength LiDAR that would penetrate somewhat into the water and would allow you to also monitor the bathymetry, as long as you don't have too much suspended sediment in the river. But the newer generation of LiDAR sensors, they measure up to 20 meters depth in rivers or in shorelines. So, for example, coastal California is now fully covered with a bathymetric LiDAR, where essentially an airplane has been flying 50 to 100 meters within the coast, and so you have a very precise digital elevation model of the shelf. This was my question yesterday with the shelf, by the way. You can zoom in even further, and you can generate digital elevation models at a very high scale, a very high spatial resolution, using terrestrial LiDAR scanners. These are examples here where you can use digital elevation models to reconstruct either buildings, or this is an area where we worked in Santa Barbara after a big wildfire. Essentially all the vegetation has been removed here, and you see the tree stumps. These are those spots here, and we have monitored this area to measure the amount of mass that has been eroded. Okay, so this was a quick intro into some applications. Let's see why we want to use digital elevation models for other planets as well. And this is really important because they are signatures of tectonic activity that you find at the planetary scale that you can identify with digital elevation models. So in other words, by having a digital elevation model of a planet, you know if the planet is tectonically active, if there are geodynamic processes or not. So it's a very, very useful piece of information. And let's zoom in to Mars. And before we do that, just a brief piece of information. I mean, you're all familiar with digital elevation models for the Earth, right? You know about the 90-meter or the 30-meter SOTM DEM. I'm certain you have heard that, right? The TandemX DEM, which is a 12-meter resolution. So that's a nearly global DEM. So pretty much there is a 12-meter resolution digital elevation model available for most of Earth. If we look at Mars, Mars is much better monitored than Earth. So we have for Mars, we essentially have a 1-meter spatial resolution DEM for all of Mars. We don't have that for Earth. So the things we can do on Mars are often somewhat advanced than what we can do on Earth, and part of the reason are political or military interests. So there is no interest in having a 1-meter DEM for all of Earth, just because that would give you an advantage that you don't want to be exploited. So Mars is much better observed and much better monitored than Earth. I thought that was interesting just because, you know, we always talk about great technology advances. Of course, we have the technology to generate a 1-meter DEM for all of Earth, but we don't do it. Or at least we would not distribute it globally. By the way, the only company that owns, or the only agency that owns the global 12-meter DEM, in addition to the German Science Foundation, the DLR, is the CIA. So 3 years ago, the CIA purchased that 12-meter DEM globally, I think for $400 million US. So that's about the amount of money that is involved in generating high-resolution digital elevation models. because of that military interest. Okay, let's zoom into Mars. Maybe the one or the other has seen this before. We will explore it later in the lab a little more. You see those clearly large-scale cone structures that you have here, and you don't need to be a volcanologist to realize that this is an old volcano on Mars, right? So what are the processes, the geodynamic processes that form a volcano? Well, you need definitely liquid magma somewhere in the core, and you need convection at the mantle scale. So this is clearly a sign that at some point when those have been formed, there were geodynamic processes. If you look at this here, you know, you could make yourself believe that this is something like the Grand Canyon, a deeply incised canyon. And what are processes that we know that incise surfaces? Well, that can be debris flows or rivers, for example. You know, it would be not realistic to assume that this has been a large debris flow, but, you know, for example, a large landslide that carved this steep channel here. You, of course, see those crater impacts as well, and we are going to look at elevations and slope distributions in more detail when we look at the real DEM. But one example I would like to show you of the high resolution DEM that exists here. This is a story that came out 2 years ago from NASA, who generated one of those higher resolution DEMs. And people have looked at shorelines and tsunami deposits. So using those high resolution 1 and 4 meter digital elevation models and optical data, you can map shorelines. So you can map the paleo shorelines of the water that once existed on Mars a while ago. And in addition to this, you can recognize deposits that represent large flooding deposits. And these flooding deposits have been interpreted to be tsunami deposits, similar to what we see in coastal Chile, for example, after a large earthquake. So this is interesting, and that's another piece of evidence for water on Mars. Just to orient you, this is the end of that large, I'm switching back. This is the end. We are looking at this region here. This is the region where we have that outlet of that big canyon. You know, again, I don't think you need to be a marine geologist to realize that this mimics somehow a shoreline, right? This is something that, you know, that's what everybody would agree upon. But, you know, there's also quantitative geomorphology that lets or allows you to put that in numbers. So people have mapped the shorelines, and they have mapped the different generations of shorelines. And here you can also see the outlet of that big channel. Okay, one other point about Mars and why it's great to work there is that we have galley erosion on Mars. And this is often associated with water that is frozen as ice below the surface, that is melting, and at a certain point is allowing liquid water to flow and generate those gullies. And, you know, this is something that we can model. This is something that we can describe. And essentially, we can identify how much water has been there to generate those gullies. Okay? Those channels are actually fairly large. These are a couple of meters width here at these scales. So yeah, it's not just, there's no scale on there. But these are you know, on a hill slope features that establish. Another application of digital elevation models for mass movement. So we talked about ice a little. We talked about rivers and water. Another big transport process on Earth are aeolian transport processes. So wind erosion, wind transport. And we have the same on Mars. And the great thing on Mars is that we have those great digital elevation models, and we can map dunes, and we can have digital elevation models from different years. So those are 2 or 3 years apart. And by differencing those digital elevation models, we see how much sand is being moved. So in other words, we can make a mass balance. So those red and greenish colors essentially identify negative or an increase or decrease in the elevation, which just means that we are transporting material forward. So using these data, people have calculated wind velocities and mass transport on Mars, for example, and that then is being compared to the rates on Earth. You know? And one thing that has been observed that the aeolian transport rates are much higher on Mars, just because there is a much thinner or no atmosphere, so the viscosity is lower, so you can transport significantly more material through the atmosphere. So in other words, that tells us that if we want to do landscape evolution modeling on Mars, we need to have a really good erosion law for wind erosion. Otherwise, we won't capture the main transport capacity. You know, it's the same as when you run a landscape evolution model on Earth and you don't do glacial erosion. It just will not work. You need to include glacial erosion, otherwise your landscape will, at the planetary scale, would not look realistic.
Excuse me.
Okay, let's, yeah.
So going back to the previous image, so would you expect that all this aeolian deposit to cover up these guys if they are not active? This stream,
yeah.
these channels, should they get covered up? I have two questions. One, that should they get covered up with aeolian deposit if they are not active anymore?
So those are features that will remain for several years and decades, and then they get essentially diffused out by the aeolian erosion.
And another question is, if these all channels are bringing water down, then wouldn't we expect a bigger stream running down the valley?
Yeah, I rather would call it an ephemeral stream. So it's essentially water. So you have ice, so there is ice sitting below the surface. And if you have certain pressure and temperature conditions, that ice melts. So you have a stream that runs, but because you have no atmosphere, that water is immediately evaporating. So essentially the stream dries out just by evaporation. So that's why you don't form those massive.
I get it. Thank you. Thank you.
Massive rivers. Yeah. So it's a very different process than on Earth. You know, so if you model those, you need to make sure that you have the proper evaporation term in there. Okay, let's switch back to Earth. And one thing I would like to point out here is that you know, not only the topography that we are also familiar with, but also the bathymetry. That in order to understand some of the geodynamic processes, we also need to look at bathymetry. So the elevation below the oceans. And that, by the way, is one of the main reasons why it took so many years or decades until Alfred Wegener's plate tectonics theory has been accepted. Just because in the 1920s, when he proposed this theory, there were essentially no bathymetric data available. So no one knew what the ocean, or how it looks like below the ocean. Until in the Second World War, when the submarine warfare has generated much more precise surveys of the ocean grounds, not until then we knew that, oh, there is an ocean spreading ridge. Those spreading ridges are higher those spreading ridges are higher here because the material is warmer. The material starts to cool, it gets denser, and then it gets deeper at the passive margin corners. And also the subduction zones have been perfectly monitored with those devices. So only since the 50s and 60s, we know about bathymetry, and that's one of the core things that supported the plate tectonic theory. So identifying these signals tells you something about a geodynamic process. I should say, and we are coming back to this, that nowadays you can measure some of the bathymetry or the large-scale bathymetry through satellite information by doing gravitational measurements, by essentially looking very precisely how the surface of the ocean is changing, because if you have more mass sitting at the bottom, it essentially attracts the ocean surface, and that slightly bends, only a few centimeters to meters. But these are differences that can be measured with modern modern satellites. Switching through this here. And coming back to Earth and zooming into what we are going to do later on too, I just wanted to briefly tell you that modern digital elevation models not only measure the surface of the Earth, they also allow you to measure the surface or the height of vegetation, canopy height layers. And this is something we will be doing with the LiDAR DEM. This is an example of an area near Santa Barbara. These two catchments have heavily burned during a big wildfire. And this is a vegetation height map. So essentially, I've been taking the first return and the last return of the LiDAR data. And the blue areas here indicate high vegetation, 5 meters and above. And all of the reddish, yellowish colors are the areas that have essentially completely burned. So all the vegetation has been removed. And only vegetation remained in the areas near the river just because you had more water content there, and so this didn't burn. So these are is another example of an application of digital elevation models. So let's dive in a little deeper and let's look at what are variables that we can derive. I'm sorry, yeah.
Yeah, can you go back to your previous slide? Here, blue color is the water, basically. No? You are saying it is a hive.
This is vegetation height, meaning that the brownish colors are less than half a meter vegetation height, and if you go into the greenish, bluish colors, you have 5 meters and above vegetation height. And I'm associating that vegetation height with the water availability that you have in those areas. So those are streams, and because they accumulate the water, you tend to have more water in the stream areas, and then you tend to have higher vegetation, and that higher vegetation has a higher water content, so it doesn't burn during a wildfire. And this is why this vegetation remained here after the wildfire. Essentially, the flames jumped over the valley and then affected the vegetation on the other side of the hill slopes, but they did not burn the wet trees that were near the stream.
Could you just clarify the unit, the height unit, because I see a value like 444 on the index.
This is, the units are in meters, 0 to 5 meters, so essentially less than 5 meters. Half a meter to 1 meter, 1 to 2 meters, 2 to 3, 3 to 4, and then above 5 meters. And the 444 is, of course, not a vegetation tree. It's essentially a bird that was several hundred meters above the terrain. And this is what happens if you don't properly filter your point cloud data. You get a bird in there, and then you end up having a very high elevation difference, but that's no real elevation difference.
Thank you.
Yeah. Okay, let's dive into some of the ways how we can use digital elevation models in a more quantitative way. I briefly want to talk about what are the variables and parameters that we calculate from a gridded digital elevation model. And of course, we have the height itself, right? That is the grid value, the Z value. We can calculate aspect. Aspect is the direction the terrain is facing. And how we do this, I will show this in an example. Or we can look at the slope. And slope is a gradient. You can take also the second derivative, which would be the curvature, right? That's the curvature of the surface. We will do this in a second. So, but how do simple GIS software suites such as ArcGIS or QGIS, how do they calculate aspect and slope? You do that by using, for example, a 3x3 kernel or window, and you then fit a plane to this, and the direction the plane is facing gives you the aspect. So that's a very simple approach to identify what is the degree that your plane is fitting to. We will come to this in in a second and we dive in a little more. But just envision that in order to determine the direction that a terrain is facing, you always need to know the neighborhood. You know, it's not a single-based grid cell, you need to know the neighborhood. And if you know the neighborhood, you would put the aspect value only in the center, right? How about slope? Slope is doing the same. It's using a 3x3 moving window. And for example, if we have the 8 neighbors surrounding our cell in the middle, we know the distance along those grids. So north, south, east, west would be the distance of 1 times the cell size. And if you go diagonal, it's just the square root of 2, right? So that's, that will be the distance. And then that means that if we know the distance and the height difference, we can calculate the slope. So if we do that for an example, these are elevations in meters. So our center cell is 332 meters high. Then we have one cell that is 340 meters. And down here we have one cell that is 320 meters, for example. So how do you calculate the slope versus every other cell? Well, you just take the elevation difference, 340, 332, the elevation difference is 8. And the distance here, the x distance, rise over run, right? That's the slope, is the cell size, 30 meters times the square root of 2 because it's diagonal. So we are here at 42.47. So if you do this for all slopes, you end up being able to calculate the slope. So this is not the slope here in degree. That is essentially the slope in meters over meters because we have taken the x distance in meters and the height distance in meters. So if you take the tangents of this, you would then be able to calculate that into degrees. But the point that I want to get across here is that you have 8 slopes, right? You have 8 surrounding cells. So what is the slope value that you store? And the general convention is that you only store the steepest slope. So in other words, even though you have 8 values, you only store the steepest slope, and the steepest slope of the 8 neighborhood here is minus 0.28. And that's the single value that you store in that grid cell. So even so, you know, you would have many additional slopes in the x and in the y direction. The general convention is that you only store a single slope. That is at least what simple ArcGIS and QGIS applications do. There are more sophisticated ways, and that's where I want to dive in, just because I think it's important to understand how slopes are being calculated, because pretty much every landscape evolution model depends on slope in some sense, and even glacial models. So how would that work? So we can look at that in a slightly different fashion. Usually you can say that you define slopes as a function of gradient in the x and in the y direction. So you have a grid, right? X and y. And if you want to know the slope, you just take the square root of the sums. And if you then take the arcus tangents of it, you would also get the slope in radians or then in degrees if you want to, right? The key for any of those, so this is an analytical function that you can use for a functional surface as well, right? You don't need to think as a grid world. You can also have a two-dimensional function. But, you know, DMs are normally gridded. So the core thing for slope calculations to work out are those gradients, the gradients in the x direction and the gradient in the y direction, okay? So most of the emphasis and most of the research that is being done in estimating a more precise slope is how do we best generate those gradients. So either fx, fy, or dz dx, dz dy, right? So this is essentially the way how you would address the problem. So how can you best determine those slopes? And there are many ways of doing that. And different software programs have implemented different ways of calculating slope. Yes?
So aren't we're taking only the x and y values, that will be your latitude and longitude. So what about elevation? Aren't they used?
Well, we make the simplified assumption here that we have a grid, and the grid stores the Z elevation, and we are only looking at the slope of the elevation. We are not, of course you can take slopes in other directions as well, but we assume we have a surface and that our variable is V, the height. So the slope that we are determining is, because we are on a grid, the distance in the X is always the same, the distance in the Y is always the same, but the distance in the Z direction is changing. So taking the slope in the X or in the Y direction along that axis would not be very, very helpful, because that distance is always the same.
So a slope map will be different than a hillshade map?
The what? The?
A slope map will be different than a hillshade map?
Yes, yes, yes. So a hillshade map is essentially assuming some height of a sun. You have a directional value of the sun that goes from 30 to 360. That's the aspect. And then you have a height value at what height you put the sun. And that allows you to calculate a hillshade value. A slope map gives you the local terrain slope. So, you have those nice squares here. If I would like to know the slope of this point here, I look at the neighbors, and wherever there is the steepest direction, I put that slope into the center. And then I go to the next pixel and I do that calculation again.
So then that will depend on how many neighbors you are taking.
Very true. And normally you take a 3 by 3 neighborhood, but you don't have to. You can take a 5 by 5 or a 9 by 9 neighborhood. If you're interested in having a slope that is somewhat smoother, for example, a slope that not only takes into account the immediate neighbors, but also the neighbors further down, you can take a 5 by 5 window. Some people do that. We do that, for example, to derive a shallower, a smoother slope. Because sometimes the DEM is a little noisy, right? There is a little noise in the digital elevation model, and if you take the immediate neighbors, you include that noise. But if you say, well, I would like to average over the 25 neighbor pixel, then you get a smoother slope. It will also always be lower, that slope, if you average over a larger area. Yeah? We will do that in the lab exercise. We can use different kernels, right? So I'm going to walk through one of this calculation, and maybe that then becomes more clear. So by definition, you take the surrounding 9 pixels. And if you want to calculate the slope, the big question is always, how do I derive the slope in the X direction, and how do I derive the slope in the Y direction? And the most classic approach is to just take this line for the X direction and the upper one for the Y direction. So essentially, if you want to derive the slope in the X direction, it is the value of the height in 6 minus the value in the height of 4. And because you do 2 steps here, you divide it by 2 times the grid cell size. So that will be your slope in the X direction, right? Very simply, numerically, like doing a derivative by hand, right? It's almost like a forward modeling exercise. So that is the slope in the X direction, and you can do the same in the Y direction. Is the height here minus the height of this divided by 2 times the grid cell size, because we have done 2 steps. So this is one approach, but of course there are more sophisticated approaches that take into account finite differences, for example. And then those finite differences can be weighted by distance as well. So I'm not reading the equation. I just wanted to let you know that there are approaches that would take into account the full neighborhood. And then this is weighted by the distance to the center cell. So the cells 1, 3, 9, and 7 are a little further away than the cells 6, 8, 2, and 4, and therefore they get different weights. So that would give you, you call that a finite difference weighted squared distance approach. Alternatively, you can also fit a polynomial to the surface. And this is what you do when you want to measure curvature. So when you have a point cloud, for example, you fit a polygon of the second order to that surface, and that term gives you the curvature. So you know how curved your surface is, and you can derive a more precise curvature. So this is just an example of you can have you can use a second order or maybe a third order polynomial if you want to, and you derive the slope and the curvature of that. That, of course, means that gets pretty computative intensive or also expensive in the way. If you're fitting a polynomial to every 3 by 3 neighborhood and you have 1 million pixels, that takes a long time. So that's why this approach is the most widely used, just because it's so cheap. It's computationally so cheap that you want to use this instead of the more sophisticated ones that would take into account your full neighborhood.
So can you give us some concrete example where this does not work? You have to go for the other ones.
So if you're only interested in slope, I think this works well. This works well if you're only interested in slope. If you're interested in deriving the second derivative, curvature, this is the way to go. You want to fit a polynomial, at least the second order polynomial. I often use fourth order polynomials too, to fit that to the neighborhood, and then you have the slope term and the curvature term. And they are, you do it in a least square weighted way, so you're trying to minimize the error, so you can throw out some of the outliers if they are outliers. But generally, fitting a second order polynomial is a very good approach, but also very expensive. And I never use a finite difference weighted grid. Either I go with this, or I do a polynomial surface. The nice thing about this, the really nice thing is, and this is a paper that we published here in 2019, Taylor Smith, Alyosha Reinwald, and myself. We looked at the optimal grid resolution for topographic analysis using LiDAR. The nice thing about this approach is you can propagate the errors. So because it's so simple, because you have that simple X and Y error, you can also include the uncertainties of the elevation measurement, and you can propagate those errors. If you are going to do this with a finite difference approach, it becomes much more complicated. And also, if you would do a quadratic surface constraint, it becomes much more complicated. So especially nowadays, when each digital elevation model, each point has some uncertainty associated with it, if you want to keep track of those uncertainties, this is much better. I rather know the uncertainties instead of that I have some fit where I have no idea how good it is.
If the terrain is really smooth and topography is not varying so much, then this method or the next method, which one would be better?
Again, this works well for a simple slope analysis, and if you don't have too much noise in your DEM.
Okay, so the noise is what matters.
If you have a DEM with lots of noise,
okay.
And we will use one later on, then a least squared polynomial fit is always better.
Bodo?
Yeah.
So in case of, for this example, when we are fitting a second order polynomial for a 3 by 3 matrix, we are going to get a single curvature value. Because if you double differentiate, it will be a constant. In case of a fourth order polynomial that you suggested, we are going to get a variable curvature inside that.
So we would get, if we use a gridded approach, we would get curvature in the X direction and in the Y direction, right? And that means, there are different types of curvature. You can measure the curvature along the steepest line, and you can measure the curvature along a contour line. That's why you also call it contour curvature, along along the contour line or along the steepest gradient that's in as a profile curvature. Here, I don't know it on the top of my head, but you can combine the polynomial in a way that you can measure a profile and contour curvature as well. So you would be able to derive a mean curvature, which tells you the average curvature, but also the derivative in the x and in the y direction, right? Because you have here the ax squared and the by squared, which essentially is a curvature in the x direction and the curvature in the y direction. And you can take the mean of this, or you would take along the x and along the y direction. So you would be able to pull out the tangential and the contour curvature as well.
Yeah, but I understand for this particular curve, so if we fit a parabola, doubly dipping parabola, then it's all right. But if we are fitting a fourth order equation, like you said, you fit a fourth order polynomial to your 3x3 matrix.
Fourth order?
Yeah, fourth order polynomial. So in that case, so as we move through that 3x3 matrix, our curvature is going to change.
Well, the whole idea about fitting a higher order polynomial is, I'm only going to draw this here in 2 dimensions, just because drawing a 3 dimension becomes always more complicated. Let's say we have a surface that is like this, right? If you fit a first order polynomial through it, it would maybe look like this, right? And then you would be able to measure that curvature as an x squared value, right? If you, I'm sorry, this is a second order polynomial, of course. The first order polynomial is a line, sorry. If you then use the fourth order polynomial, you could have maybe something like this, where you have additional warps in there that allow you to capture some of the terrain characteristics, which means you are ignoring the fourth order polynomials and you're only focusing on the second order polynomials, but they would be slightly different, right? So this second order would essentially be an average of all of the points, whereas the fourth order polynomial would probably capture some more variability in there. It really depends on the size of the window that you're looking at and of the noisiness of your data. Usually a second or a fourth order polynomial works well. Either way, the differences are very small. We did an analysis in this paper, Taylor and I, for a larger area of the Santa Cruz Island, and the fourth order and second order polynomial are not that different. I mean, of course, the equation is different, but if you pick out the x squared term in the second order and the x squared in the fourth order, they are fairly similar.
I think the confusion that you are having, that you take a fourth order function, take double derivative, you're going to get a function, but you evaluate that function at a given point, right? So that function value at the origin gives you a number. That's the one you're looking at.
Okay.
So, I mean, you know, so you could ask the same question for slopes. Slope, the first derivative, you have the x terms in the fourth order and the second order as well, right? And those terms are slightly different, but not any, you know, not in a significant way. Okay, let me just come back to the slope and aspect calculation. This goes in the direction of the question with the hillshade that someone asked before. You know, so we just talked about, this is the analytical version. We have a gradient in x and a gradient in y, and the question is, how do we determine that gradient from a grid, right? And that's what we just talked about. The same question is pertinent for aspect, because we have that same gradient in the y direction and in the and this time in the z direction, right? So this is because we are looking what the aspect looks like. So these are the equations that we would use for determining the slope and aspect in degrees, and then you can change that term, and then you would have it in radians. So again, the key is how do we derive the slopes in the x and in the y direction. Okay, from that little excursion, let's just briefly look at some of the examples of what height and aspect would look like. Here we are focusing on a part in the central Andes, steep topography. You see the channel that has been widely incised here. Aspect, I think, is clear. I just wanted to point out that using slopes, this is a slope map going from low slope values in black to high slope values here in red. We can make a first statement about geomorphic process. And geomorphic processes in the sense of that we have low slopes on the valley, meaning these are glacially carved surfaces where we have the glaciers have carved out those terrains here. So this is a glacial terrain, and here we have a steep incised gorge through a fluvial erosion terrain with very steep hill slope angles. So seeing those slopes and being able to look at the distribution of slopes, we can make statements of what shapes the terrain. I pointed out before that we can turn the DEM into a flow map. I'm certain that most of you are familiar with this. I just wanted to point out that we can calculate the flow direction, and here I'm just using a simple 8-direction flow direction. So I'm looking at every pixel and I'm looking at the steepest slope, and that is the direction the water would flow. You call that a D8 algorithm because it only has 8 options of flow, and it's the steepest descent. So it's going along the steepest direction. And if you do that for a DEM, you see what the arrows look like, and you see that there is an area that is accumulating more flow from the surrounding areas, and this essentially gets turned into a channel. And we will be exploiting this later to generate river networks and do steepness analysis, for example. So if we go from the flow direction to the flow accumulation, we are essentially counting the numbers of pixels that are accumulating, that are adding up into each other. So these are the zeros, are essentially the catchment boundaries. That's where no water is flowing into, only water is flowing away. And here we see this is a rapidly increasing numbers of pixels. This is essentially the water that is being accumulated. Yesterday we heard about that you can turn rainfall into a discharge value. Well, this is exactly how you would do it. You would weigh your grid, your DEM grid, you would weigh this with a rainfall map. So you can put essentially a rainfall map on it, and then each of those pixels here, you know, doesn't have a value of 1. It can have a value of whatever the rainfall rate is. And by accumulating this, you are essentially generating discharge, ignoring evaporation and infiltration, which is of course not true, but at least it's a good first order approach. Okay. In the remaining time, I think I do half hour more. I just wanted to briefly talk a little bit about how we can generate different DEMs, and then we dive into something different. That looks different on my screen. I suppose the fonts haven't been properly converted. So, okay. So I wanted to talk about how we can generate DEMs, and I wanted to talk about interpolation of survey points, a little bit of stereo air photos and stereo satellite imagery, about digitizing topographic maps, about radar interferometry, and LiDAR. And some of those I go through much quicker because I assume that you have heard about them before. So let's talk about interpolation of survey points. And the core story here is that this is still the way to generate the most precise DEM. If you want to have a millimeter DEM, you have to have a total station or a very precise surveying instrument. Otherwise, you don't get that precision. No LiDAR and no drones can do that. So really, if you want to measure the erosion of a river, you need to do you need to use a laser theodolite or something similar that gives you that precision measurement. You can also use GPS or GNSS, the Global Navigational Satellite Systems. These are L-band signals. It's an active radar system that allows you to measure the distance or perform triangulation and then measure the distance. And, you know, you're familiar with those GPS survey equipment, and now you can envision that you're not only, this is a differential GPS survey equipment, now you can also envision that you can combine that with laser total station data that then is very, very precise. In the end, you end up getting a point cloud that you need to interpolate, and you can perform contour lines or contour line calculation or a gridding function. This is something that we will then do with a LiDAR point cloud data, so that we have those irregularly spaced points and we generate it into a grid. I really like the way that we have essentially we have a gridded floor, right? So this is a really nice way to demonstrate some things. I'm just realizing this. Okay, stereo air photos. Up until LiDAR, LiDAR got really big in the, let's say early 2000s because the lasers got much cheaper at that point. Stereo photogrammetry was the only way of generate high resolution DMs for larger areas. And it is still a very, very useful way of generating digital elevation models, just because the newest generation of air photos have 10, 20 centimeter spatial resolution. And usually you say, 3 times the spatial resolution of the air photo gives you the DEM resolution. So if you have a 10 centimeter air photo, you end up having a 30 centimeter DEM of it. If you have a 1 meter satellite image, a GOI worldview satellite image, you end up having a 3 to 5 meter DEM of it. So this is a rule of thumb. I start out with a simple air photo view, and the idea behind stereo photogrammetry is to exploit the fact that you have distortions towards the corners. You have a principal point where you have 0 distortions, and then the distortion is essentially radially increasing. So you can measure the distance from a principal point to a site, and by measuring that height here, you have the height of the building. Essentially, you can convert a distance to a height because you have the precise geometry information. That's something you do through the culinary equations. I don't want to go into detail here. I'm just letting you know that with air photos, we usually have a very precise geometric setup. The airplane flies at a height. We know the focal lengths. The air photos are taken very nicely straight top down from a nadir position. That allows us to turn those information into very precise height information. I'm not going through detail here. I usually explain this. Just culinary equations. These are the equations that are used to convert the information of the projected image to a ground image. This looks complicated, but it's really only a bunch of angles. You're really measuring angles. You just have different planes that you're observing. You have a focal plane, and you have a surface, and you are combining those different angles. So you have image coordinates and ground coordinates, and you can convert between them. So this is what the culinary equations allow you to do. I wanted to briefly talk about some of the examples of stereogrammetry using satellite imagery, just because I think, or let's put it that way. In India, I have not been successful yet obtaining stereo air photos. So I have not been able to generate a DEM from stereo air photos. In Argentina and in the Central Andes, we have been able to do that. Not in India, just because I couldn't get a hold of the air photos. So it's more realistic to use satellite-based stereogrammetry. The principle is the same. And that's why I wanted to talk about this a little. One of the first publicly available satellites that allows you to do that is the Aster satellite. And the Aster satellite has a great capability to have two cameras in the red channel that is pointing downward. You call that nadir. So you have one camera that is pointing downward, and the same, another camera is pointing backward. You call that the 3N and the 3B channels. And since the satellite is moving, the satellite is taking one photo in the nadir position, then the satellite moves, and roughly 60 seconds later, the satellite is at that position where the backward-looking channel looks at the same position on Earth. So you have taken a photo, a nadir, the satellite travels, looks backwards 60 seconds later, and takes this photo from the same spot. And so you have two views from two different angles. And that's the same as our eyes work. Our eyes make a three-dimensional image by having an angular view of the surface. We can use here 27.6-degree difference. So you have two view angles, and you can turn that into height information through the collineary equation. That has been exploited for the past 20 years, essentially, and that has led the Japanese Space Agency, together with NASA, to generate something that is called the Aster Global DEM. So combining all of the millions of images, the optical images that have been added together, you know, all the nadir and the backwards, images, you are generating a global DEM. That has several errors, but it's a nice DEM because it's generated through optical data, okay? And I'm pointing this out because there's just a new version that came out last summer, and it's been constantly revised. That's a nice contrast to the SRGM DEM, for example. You know, you can do this at a higher spatial resolution using spot data or GeoEye data. We just bought, for the Central Andes, we just bought some spot 7 data that allows us to generate a 3-meter DEM, like a 1-meter spatial resolution, and then if you add it, you get a 3-meter DEM. It's a very nice data set, but it's commercial. And I just wanted to tell you what the different look angles look like. So this is one angle, 26.8, and then we have almost a 40-degree difference. So one look angle from here, one look angle from here. So you have different shades, different valleys, but this is, it's not that bright, but usually you nicely see you have the same feature here, essentially illuminated from different angles. It's the same as having a hillshade from different angles. And you can turn those hillshade information essentially back into elevation values. I am skipping ahead, and I'm just pointing out that digitizing topographic maps is something that is still very, very useful. And I'm saying that because during my PhD thesis, which I did on the border between India and China, I ended up digitizing many maps from the British survey, 1960 British survey maps. Those have been incredibly useful. That was, by the way, pre-SRTM times. And those maps are very, very useful. And there are many glaciologists that study mass balances that still use those maps from the 50s and 60s to generate changes of glacial mass balances. So you may think that is old school, but no, it's not. It's a really nice way of obtaining information from a few decades in the past. Yeah, so those are very valuable maps, and they have been conducted by people with great field skills. So the survey points they have taken are very, very useful. And let me just dwell a little bit on the last point I would like to make here today, and that's radar interferometry. We talk about LiDAR in much more detail on Thursday, okay? I just want to talk about radar interferometry because we will be using the SRTM, the tandem-X. We talked about this before, and I would like to contrast this to the ASTA GDM, the optical derived DEM that we just talked about. If you want to dive in more detail, there is a very nice introduction to synthetic aperture radar. This is freely available here on that website that describes a lot of the details of how modern SAR data are being collected. For example, all the Sentinel-1 data, the TerraSAR, tandem-X, and so on. So this is a nice introduction. I'm just touching upon a few of those things. There is no way that I can cover radar interferometry in 5 minutes. We usually do classes that last a semester on radar interferometry. But the basic idea is that we are having two observations and they are generating an interferogram. And the example of an interferogram, you can look at the famous Young's two-slit experiment where you have one light source. That light source gets split up by the two slits. And those two slits, essentially you have the same light source. It just gets split by two slits, and then the resulting light waves that are essentially being emitted from those two slits, they interfere with each other. And that is the distance in the travel, or the distance in the travel distance that you are then recording. And instead of having those two slits, you can envision that you're having two radar observations. Either you have two satellites, or you have two radar observations that are, a couple of days or 30 days apart. And I'm saying those because the SRTM mission essentially means that you have had one radar beam on the shuttle and then an arm with 70 meters distance. So you had two sources on the same spacecraft. The tandem-X mission, the TerraSAR-X and the tandem-X satellites, they were flowing in a tandem. So they had two different satellites doing measurements very close to each other. And Sentinel-1, the currently active satellite by the ESA, the European Space Agency, the Sentinel-1 revisits every point on the surface of the Earth every 6 to 12 days. So there is a temporal distance, temporal time lag between the images. So what you can do is, what you can envision is that if you have one pass, this is now the two-pass interferometry, if you have one pass before the Earth moves, for example, and then a pass after an earthquake, you are measuring the distance, the offset in the phase. So how much further did our radar beam travel? And you can then turn that into a distance measurement. Similarly, instead of taking two passes before and after an earthquake, you can take two observations at the same time and turn that into elevation information by essentially having one recording unit and one sending unit. You do the same principle, but instead of measuring the distances, you're measuring the absolute height at this point. And let me just see. And you have the two options. You can have the single path interferometry. This is something that has been done on the SRTM mission, and I will show an image of this. Or you can have a repeated pass interferometry. This is what Sentinel-1 is currently doing. So you have essentially the same satellite that is slightly offset. Every image is being taken, 50 or 100 meters from its previous location, which is quite amazing. Thinking about, you have a satellite in 700 kilometers height. This is about the height that the satellite is circling the Earth. And every time it is at the same track and swath, it's only 50 meter in distance and space. It's quite amazing, you know, thinking about the distances, and you call that the baseline. So the baseline allows you is the distance between two satellite observations. So let's zoom in the SOTM. The SOTM is the single most successful mission.
Bodo, I had a question about this application of SAR interferometry on earthquakes and measuring the slips and all, whatever it is called, the surface movement. So, how do you deconvolve for the topography? For that, you need some DEM, and this DEM, if it is low resolution, then would you expect finally the displacement field that you are getting, it will have some errors?
So I mean, you essentially do trigonometry. You know, you can envision, you can have. Let's just say that this is your SOTM.
Yeah, I understand that calculation, but to know the, you know, because the second image that you will take, that will have differences because of the topography also. I mean, there will be interference pattern just because of the DEM, and that DEM is typically low resolution. And you are using that to take out the topography effect and see the actual displacements. So how is it done? Is there any tricks that you should do?
You usually have multiple, good point, you usually have multiple measurements. So meaning you not have a single measurement, you have multiple measurements, then one is being used to remove some unknown phase, which may be the topographic phase, and then the next measurement then may be used for deriving the actual elevation. Ideally, you know, the more measurements you can use, the better it is. TandemX ended up surveying every location on Earth 8 to 10 times. So there's repeated information on it that you can then use to optimize your results. Just because, you know, just to correct for all of those topo phase effects and others. Yeah. So a single radar measurement may only be somewhat useful. If you have multiple radar measurements, it becomes very, very useful.
Excuse me.
Yes?
You have said, you have listed out various methods to generate the DEM. Basically, I'm interested in that we go to the field and do measurement like GPS, or from contour we are generating. So basically my question is how to decide what will be the cell size of DM when we in the field. I think we cannot strictly go point by point strictly in a line. We have random heights data, and in contour also we have such randomness. So how we decide the cell size and how to generate basically DM from this
finding the optimal grain size, the optimal cell size is a tricky thing. Taylor Smith and I, we spent 2 years thinking about an optimal grid cells, and we are not satisfied yet with what we have. But that was at least the first approach, the one paper that we had. So this is still an unresolved issue. The way I would think about it is, what is the best cell size concerning the uncertainty of your data? I don't think we should think in grid resolution. I think we should think in uncertainties. We should think, how precise can I measure the elevation of my point? And the SOTM data has every 30 meters, it roughly had a measurement. So that's why the initial SOTM data set has a 90-meter spatial resolution. You just roughly averaged a 3x3 moving window, más o menos. And then you get a 90-meter spatial resolution. But you can use the same data to generate a 30-meter DEM. The question is that any better? Is that then better, having a 30-meter DEM with one measurement for each grid cell? And then the question is, it depends on the roughness of your terrain. If you have very flat terrain, then likely having a 90-meter data is better, because you're averaging over three samples, or 3 by 3, 9 samples. If you have very rough terrain, then sampling every 30 meter may be more representative for the terrain, taking into account that the uncertainty is higher, but the uncertainty then should be lower than the relief of your, or the roughness of your terrain. So, finding the ideal DEM resolution, really, you need to know the characteristics of your terrain, the relief, for example. And you need to know the uncertainties of your data. We can dive into this afternoon if you're interested in it. It's not an easy question to answer. And I don't think there is the optimal grid cell size. There is a grid cell size that you can work with and that is reasonable, I think. But so what we learned from the study of the LiDAR data on the Santa Cruz Island is that I rather would go to a coarser grid resolution. So instead of a 1 meter DEM, I would use a 3 meter DEM, but with a higher precision. So for most of the processes, the geomorphic processes, landsliding, river incision, a 3 meter DEM is fine. You don't need a 1 meter DEM. I rather have a 3 meter DEM that is very, very precise, where I know the uncertainty very well, instead of having a 1 meter DEM, which has a much larger unknown uncertainty. But again, it depends on the processes that you would like to measure. If you're interested in deriving channel width from gullies, then you likely want to have a very high resolution DEM. If you're interested in general channel slopes, then maybe a 3 meter DEM will work just fine. Yeah?
While you were digitizing the old contours of the maps
The what?
the contours from the old maps.
The contour, yes.
Yeah. Most of these old maps, they use MSL for these type of contouring. So how did you change the base? Like from it? We normally in RTK or these things, we used a ellipsoidal base. And in this, we used an MSL. So how did you, what did you do to change that?
Well, many of the contour lines, are drawn by the cartographer in the field, right? Where you have a few measurement points, and then, there is a lot of guesstimation in it too, right? So the contour lines, they look all smooth. They don't necessarily need to be that smooth. But the idea is that we digitize the contour line, and that the contour line is an isocircle, following the same elevation. And so you have essentially elevation points all along that contour line. And then you're asking how to turn it into a grid, or?
No, see, these contour lines, they are made from MSL. They are with respect to.
They're made of what?
They are in respect to mean sea level. These elevations, the contour elevations, are from with respect to mean sea level. So how are you changing it to the ellipsoidal height? Because that's what we normally use in every.
Good question. So that's where the different geoids and the different descriptions of the Earth's surface come into place. And we would need to talk about datums and geoids in order to be able to convert the local measurements to something that can be compared to satellite-based measurements.
Yes.
Maybe I explain it that way. Maybe I say that the earlier SOTM mission, or the earlier data from the SOTM mission, was referenced to the WGS84 geoid. There is a new mission, a new processing of the SOTM data, which is called the NASA DEM. They just came out with it last year, which is referenced to the IceSat data. An IceSat is a laser, is a spaceborne laser that has a very precise absolute elevation information of the Earth's surface. So everything has been referenced to that IceSat data, and that allows us to remove some of the geoid effects as well. So many of the modern data sets, TandemX, SOTM, they are referenced with respect to IceSat. Now there's the IceSat 2 mission, so there's a continuation of it, which allow you to do a much better local referencing. So if you have your topo map from the 60s, you essentially, ideally, you would be able to link it to an ISAT measurement point. For example, if you take a flat river terrain where you have at least 100 by 100 meters fairly flat terrain, you pick out the ISAT elevation and you use that as a reference elevation. And that then allows you to very nicely tie in your map to the existing satellite data. That is always a little tedious. You spend quite a bit of time finding the ISAT points, but then you have a data set that perfectly matches with your radar-based data, for example. So it would be the right thing to do.
Okay, I will try, because I met this problem when I was surveying UAV surveying area which has been done by the which is an ONGC. It's a long old this factory. So the area which was surveyed, that had the elevation in MSL, and I had this drone data, so it was like in geoid, so that made some problem. No, I haven't used topo sheets.
Yeah, that's another thing.
Yeah. टोपो शीट उनके पास टोपो शीट नहीं था, ये लोग समझ ही नहीं सक रहे हैं मैं क्या बोल रहा हूँ, वो तभी
there would be a way to do a functional conversion to convert between the different datums. That's one way, because the datum is nothing but a functional description of a surface. You have the ellipsoidal description, but I think the future, but there may be still centimeters or meters offset, just because maybe back in the days things have not been measured that precisely. I think the future, in order to link some of those older surveys with newer surveys, you will be using ISAT or ISAT2 data. The ISAT2 data specifically is very useful, so that you have one common reference frame that you link your data to, and then you would circumvent some of the uncertainties that exist. You say what? No. Globally. Yeah, globally. Yeah. Otherwise, no. I used ISAT data continuously in Argentina and in the northwestern Himalaya, the older ISAT, and now the ISAT2 is also fully globally, and the data is all freely available. It's a little tricky to work with it. It's not that intuitive, but it's all freely available, and it's globally.
Sir, what is the vertical accuracy of ISAT measurements?
You say what, please?
Vertical accuracy of the ISAT data.
ISAT is a spaceborne LiDAR, and which then has a footprint of roughly 80 to 100 meters. So you get an average return signal over a 100-meter surface. If you have a flat surface, your uncertainty is in the centimeter range. So it's, for being spaceborne, it's very, very precise. But if you have lots of vegetation on your surface, then it gets a little trickier to determine the bare earth signal. But if you have no vegetation on it, it's a very nice, very useful data set. Should we take a break? Yeah, sure. Yeah. Let's take a break, and then we continue with a little bit of SOTM and TandemX in what, 20 minutes, 30 minutes? 15 minutes, okay. So, welcome back. In the next 20 minutes or so, I wanted to talk a little about different radar-based DEMs, and I also just added a comparison between different digital elevation models that I would like to talk more in detail about. I just wanted to show this slide here and the artist's depiction of the space shuttle. This is the way how it really worked for the space shuttle. You had the 70-meter long sidearm of the space shuttle, where you had a radar antenna and you had a radar transmitter and antenna on this space shuttle. One thing that you notice when you look into the SOTM data into more detail is that there is lots of noise in the SOTM data. And part of the noise of the SOTM data comes from the fact that you have a 70-meter long arm and you have a space shuttle that has to accelerate and de-accelerate. So what happens in space, because the laws of inertia still are applicable in space too, so if you accelerate something or if you de-accelerate something, that arm is wobbling. And then if your arm is wobbling, it means that you get long wavelength jitter in your SOTM data. And that essentially is derived from the thrusting of the space shuttle, the acceleration and de-acceleration. So this is one part of the error source if you look into SOTM data in more detail. And I will point this out later again. So the SOTM coverage is unfortunately not fully global, but almost. And it is up to date, one of the most useful data sets, even so it has been collected now 20 years ago. Yeah, pretty much exactly 20 years ago, 2000 in February. Yeah, interesting. Okay. Just a word regarding the data amounts. Now I know that some of us have desktop computers with more than 12 terabyte hard drive space, right? Back in the days, 12 terabytes means that you needed an entire room full of hard drives to store these data. Yeah, so this has been a significant and major infrastructural or cyber infrastructural approach in order to deal with all of those radar data that have been generated. The SOTM mission is a C-band radar, which means that it is not a very well penetrating vegetation, but it is generally a fairly robust signal. The more modern version of a radar-based data set is the TerraSAR X Tandem X mission. And essentially, these are two satellites that are exactly the same. The German Space Agency put them up. The TerraSAR X is active since 2007. Tandem X was launched in, I think, 2014 and then collected data since then. And for the time from 2015 to 2017, they flew in a special tandem mission. You call that, they were having the so-called double helix. You know the genetic code that is being, the depiction of the genetic code that is rotating in a way where you see the different DNA bases. This is the same flight path that those two radar satellites have been using. So they have been acting both as a receiver and sender. So they have been flying in the so-called bistatic mode, meaning that both satellites have been receiving the reflected signal, but one satellite always has been sending the signal. So you had essential multiple interferograms that were generated with one overpass. We had the question earlier about the topographic face. You can remove part of the topographic face by exactly this acquisition, right? You have one satellite sends off and receives, and the other satellite just receives. So you know the exact baseline, you know the distance between this, so you can back calculate any of the artifacts. I'm not going into much more detail here just because this is partly a commercial product and it's not really applicable to a global based analysis, at least not at the original 12-meter resolution that those data have been released. The data itself are being collected at roughly 1 by 2 meter spatial resolution. That's a radar resolution, and then it's being multi-looked 5 by 6 times. So, 1 to 2 meters, let's say 2 meters multiplied by 6, that's how you end up with a roughly 12-meter spatial resolution. So it is already an average signal. If you go into the raw data, you would be able to generate a 3-meter DEM, for example, but that would be much more noisy. And the commercial product that is quality assessed and that is being released with an error report and all this kind of stuff is a 12.5 meter. And this is what is called the TandemX World DEM, for example. There have been studies looking at the accuracy of this DEM, and I would like to show one example of what you can do. I do understand that maybe some of you even have been doing those kinds of studies yourself. I just wanted to show a comparison of different digital elevation models of what we did in the Central Andean Plateau, which is essentially an area very similar to the Tibetan Plateau. High elevation, flat, but you also have margins. You have the plateau margins, which are very, very steep. Just real quick, I used this was a study with Ben Purton. He is a PhD student who just defended on Friday his thesis, so before I came here. We used the SOTM C-band, the original data that I was just showing, the ASTER GDM. I showed this before too. We generated our own ASTER stack by using multiple ASTER overlapping scenes. We used the ALOS World 3D DEM that's called the AW3D5 that has the 5-meter is a commercial one, so we had to buy this. The 30-meter spatial resolution is a public available one, and I just heard there is a 12.5-meter spatial resolution one now being released. However, I'm not too happy with these data, and I would tell you in a second why. And then we used the single teraSAR X tandem X scenes. So the same scenes that the DLR used to generate the tandem X DEM, we manually process them at a higher spatial resolution to see if we can get more data out. So this is radar interferometry using the co-aligned imagery. And then we use the tandem X DEM. That's the 12-meter DEM. We obtained this through a research contract with the DLR. Otherwise, we would not have been able to pay for it. One way to visualize the uncertainties is to look at delta H values, delta height values compared to a reference data set. And in the Andes, I've spent many years collecting differential GPS data. And in fact, I collected more than 200,000 individual differential GPS points. So I'm using that as a reference data set to compare the TandemX, the 30-meter global DEM, the GDEM, and the SOTM-C data. So what you see here is the DH, as I call it, is the delta H, is the DEM minus the differential GPS elevation. Okay, so I have a reference. This is our differential GPS and the DEM. And if everything is correct, this would be 0, right? Because the height difference should be 0. But the height difference is not 0. It's somewhat maybe semi-Gaussian distributed around the 0 value. So looking at these plots, we can look at the quality of the data set. So meaning that the closer the data to the 0, the better it is, right? The wider the Gaussian function, the more uncertainties you have. And the first thing that you see is that SOTM, TandemX, and the red global DEM, they roughly overlie a little. If you look closer, TandemX is the most accurate one. It's the closest one to the 0. If you look at this gray curve here, this is the GDEM, the ASTER GDEM, which clearly has a much larger uncertainty than the other two data sets. This is an example where we generated it, our own ASTER stack, where we manually quality control. So the algorithm that is used for the GDEM2 is an automated algorithm. So it's doing stereophotogrammetry automatically. There is no human being that checks on the quality result. Here we did a stack with 8 individual aster images and did manual quality control. And we see that doing the stacking, we end up getting a narrower distribution than the automatic algorithm. But it requires more work, right? So you have to spend more time on it, but you are able to extract even more information from the aster GDM. Whereas when you have a single scene, the red curve is a single scene, this is fairly widely spread and is not very accurate. So in order to generate a more accurate aster GDM, you need to have at least 5, 6, 7, or 8 scenes. But you have those globally at every point because you have 20 years of data. So that's doable, but it would require more work. So this is a view of the entire area of the Central Andes. So those differential GPS points, they are between 1,000 up to 4,000 meters. So it's a large elevation range where these data have been collected. A somewhat more realistic way to look at the differences between the data is to separate it out by slope, because higher slopes tend to have larger uncertainties, and that is the case for the SOTM DEM. And when we plot the data versus slope, so here is a slope going from 0 to 45 degrees, like flat to steeper terrain, and here I'm looking at the DH. So I'm plotting that height difference versus slope, and I'm binning it by 1 degree bins. So if we have slopes less than 5 degrees, the height difference is almost negligible. We have very low height difference. If we go to higher slopes, you see that those black lines start getting bigger, and you get bigger and bigger uncertainties, just because the radar data has more problems deriving slopes from steeper terrain. The blue dots here, they show you the number of points that we have per bin. So here we have quite a few points, and then of course the terrain steeper than 30 degrees slope, we have less points, just because I'm also not walking up 30 degrees steep terrain all the time. So there's a limit to the reference data that I collected. Anyway, I wanted to show you this, and keep in mind that the 0 to 5 degree on an SOTM is fairly well, and then it starts to get more uncertain. Let's compare this. Yeah.
Previous slide. In the previous slide, is this the vertical? Is this the vertical uncertainty that is showing here?
It's a vertical. It's only vertical distance. So we spend time on perfectly aligning the DEM before, and so you need to do that. Otherwise, you can't do that comparison. So we perfectly aligned them, and then we looked at the height.
Okay. So it seems the vertical uncertainty is around 20 meter plus minus.
Well, I mean, you would probably give that as a sigma. If this is a Gaussian distribution, you could calculate the standard deviation of it, and the standard deviation 1 sigma maybe would be then here, I don't know, 7, 8 meters. We have the exact values in the paper.
Yeah. So now I wish to understand that in the few slides back, you were explaining about INSAR, interferometric SAR data. Suppose there is a displacement of, let's say, less than 1 meter in the surface, and we know that there are error of the plus minus 20 or 10 meter. Then the less than 1 meter displacement, how one can able to see when you do INSAR data processing?
Well, there is radar interferometry that looks at relative height changes, and you can measure relative height changes at the millimeter or centimeter level. For example, you can measure the hydrological warping when you have a pump, you drain you pump groundwater, the surface of the earth is slowly warping down. Between earthquakes, you can measure offsets. So those are relative height measurements, and those can be at the millimeter or centimeter level. Here we are looking at absolute elevation measurements, and that's slightly different because you only have a few reference points, and then all the other information is being obtained by essentially unwarping the radar interferogram. And there are certain uncertainties associated with it. No data is perfect. There may be a little bit of noise in there. There may be atmospheric water vapor, atmospheric delay, ionospheric delay in there. So you add uncertainties during the processing. Maybe the positioning of the satellites is not super precise, it's only precise. You know, so there are several error sources that then end up adding to the total product. And I think I would need to look it up what the official uncertainty of the tandem-X DEM is, but I think they say plus minus 10 meters or something. So they give a fairly large uncertainty because of that reason. And you know, and another thing to keep in mind is that when you have a slope terrain and your grid cells are these sizes, right? Let's say these are your 12-meter grid cells, and you essentially measure the mean elevation of that 12-meter grid cell. Is it really the center that you're measuring on a slope terrain, or are you getting more return signal from the upper part, less from the lower part, and therefore you are not getting the mean elevation of that grid cell? That grid cell may be biased towards an elevation, and that's exactly what happened with the SOTM data. So there are several error reasons.
Thank you.
So essentially this is better. Essentially what these data show you, that both the SOTM and the tandem-X, they show you that there is a big peak at a couple of 100-meter wavelengths, which is essentially a valley. So you can envision this is a valley which has a spacing of a couple of 100 meters. This is what we would expect, right? Because this is taken from a mountain valley. And we don't see much noise at lower pixels. We see a little bit of noise here. And these are only 1 or 2 pixels. That is essentially the interpixel noise that we have in SOTM data. We don't really see that in tandem-X data. But if we go to the ALOS data, this is the commercial 5-meter data. This is a product that we purchased and we paid big bucks for it. But what we then observe here is that we have multiple repeated patterns of the pixels. So in 2 pixel distance, 10 meter, 3 pixel distance, 4 pixel distance, and 8 pixel distance, we see patterns that are essentially related to an inherent data problem with the ALOS data, because there is essentially a repeated noise pattern in there that is being added at 2, 3, 4, and 8 pixel distances. And that clearly is not something that is related to a real geomorphic process. That is noise in your DEM. And you certainly need to filter these data before you can use them for curvature calculation, for example. You know? Because if we do curvature calculation in 3 by 3 pixel distances, we know every 3rd pixel we have a noise pixel. So whatever you fit into your kernel, it will be biased by noise. You know, that just as a side note that you know, this is marketed at 5-meter spatial resolution, but I would not want to use these data. These data are better, even though the spatial resolution is lower. And this comes back to the optimal resolution question. Maybe the 12-meter DEM data is better than the 5-meter data because it contains less noise and is better in representing the surface feature. Yeah, so not necessarily the lowest number in the highest spatial resolution is always the best product. So that was essentially the message that I wanted to get across here. Okay, I mean, I could continue to talk about DEM comparison, but I don't think that at this point is very helpful. We may be able to come back later to this. I think it may be a good idea if we get our hands dirty with some data now. So my question is, does everybody have a laptop available? Then maybe it may be a good idea that we start to derive some simple DEM analysis based on Python. Yes?
I was just wondering, what are the smaller peaks that looks like they're equally spaced in log scale?
Yeah, you have different. Let me pull out. I did not put this in here. 1 second. Give me 1 second, because I have this. So the topography of what the region that you were just pointing out is this catchment, and we have valley spacing that is in this direction. This is a couple of 100 meters, and then we have valley spacing in this direction, which is a little bit longer. So this is why you had multiple frequencies in there. Yeah, so that's essentially the terrain. And since I'm at it, let me just show you why. So this is, if you zoom in to identify the error that I just talked about, those frequency changes, this is just 1,000 meter. So it's very, very zoomed in. SOTM, Tandemax, 30 meter Tandemax, 12 meter Tandemax. The colors indicate curvature, concave, convex curvature. I just wanted to point out, this is a 5 meter data, and you see that there are lots of speckles in the data, and those speckles are just issues that when you do the stereophotogrammetry, sometimes the matching doesn't perfectly work out, so you get a much noisier surface that is not real data. This is just the issues that you have when you're matching the points. And you know, you also have other artifacts that occur in in our single Tandemax. Exactly, the striping. Yeah. You have other.
Thank you.
Other issues.
And it seems like these speckles also have some aspect dependence. Looks like.
Yeah.
Thank
you. You know, you could also say that if you wouldn't know what you're looking at, you could also interpret this as a much more bumpy hill slope, right? But that's not the case.
Right.
So that's why, you know, I like to look at this example. You could also say, oh, the hill slope is much rougher here. But in reality, a lot of these is actually data noise.
Thank you.
Okay, before we get going here, I just wanted to point out, if you go to the GitHub webpage and you go into the directory, or actually on the base page, I have I'm going to do my screen here. Hold on a second. How can I copy this? So I just wanted to point out, if you go to the GitHub page, I prepared a document for you that is called Q Geomorph Workshop required software. And on that document, if you click on this, on that document, I describe the steps that are necessary for you to install some of the software. So we are relying on a Python environment, and who has not used Python before? Are you familiar with MATLAB? Some? Okay, there are great similarities. Let's walk through some of those things. So what you would need to do is install Anaconda. Anaconda is an open source Siphon distribution. And
Hello? Okay, so I only have one hand now. Let's see if that works. You can open your Spider editor, and I'm going to walk you through it very slowly. At the same time, you can navigate to the GitHub directory. Geomorph DM as the Gaussian Hill, and there is a Python file that is called Gaussian Hill _ Gaussian Hill.py, and that is essentially the individual commands that we are using. And let me just make this a little bigger. So I'm going to, can everybody read this? I'm going to walk you through here, and I'm doing this really slow, and I do understand that some of you may be familiar with Python, so just bear with me. So Python, this editor Spider, is the same as essentially a MATLAB environment. It allows you to have an editor here, and here would be your command line. This window here would be your command line, and you can use it the same way as MATLAB. Does everybody have Spider open, or is there a problem with opening Spider? Working? Oh, okay. Yeah, no problem. Okay, so the first thing we are doing is we need to let Python know that we are importing certain modules. So Python is a programming language. It's not developed for scientific purposes. It has been developed for all kinds of general programming purposes. We are just using it in a scientific context. And so we need to let Python know that we want to do science. And one of the core things to do is let Python know that we want to use a numerical package, and that is called NumPy. Numerical Python, and that NumPy package has lots of great things, taking derivatives and all this kind of stuff in it. So we need to import this. We need to let Python know that we want to do numerical analysis. So we say import NumPy as NP. So I could import NumPy, and then every command, everything that is included in NumPy, I could access by NumPy dot and then the name of the function, but then I always have to type NumPy. So I'm making an abbreviation of NumPy NP for NumPy. Yeah? And then I would like to import the possibility to plot, to make plots, to visualize things, and that's what I'm doing with the matplotlib. So mathematic plotting library, that's what it stands for. I'm importing the pyplot option, and I'm using a short version PL because I don't want to write pyplot always. I just want to write a PL as a short version of it. Okay, so far so good. The next couple of lines is a function. I am defining each of the each of the analytical plots as a function. And I assume this is the same as a MATLAB function, okay? It's just the syntax is slightly different, but def stands for define, and I'm now defining a function that is called Gaussian Hill elevation. That's essentially the Gaussian Hill. And the Gaussian Hill takes two parameters. One is the parameter n, that's the number of grid cells, or the spatial resolution if you want to, and the parameter b, which just tells us from where to where I want to go. In that simple example, I'm just saying, let's draw a grid that goes from minus 2.5 to plus 2.5. So if I'm doing this here, So the way I'm defining it is I'm saying I'm doing a grid from, in the x direction, from minus 2.5 to plus 2.5, and in the y direction the same, minus 2.5 to plus 2.5, and I'm doing it in numbers of steps of n. So if I say 100, if I say n 100, I take 100 steps between minus 2.5 and 2.5. If I say 1,000, I take 1,000 steps. So that's essentially how I define my spatial resolution, okay? So I'm doing this by generating a vector. This is linear spacing, so I'm using a NumPy function that generates a linear space between minus 2.5 and plus 2.5, and n is 100 times, or whatever number we choose. So we do this in the x direction, and we do the same in the y direction, and we grid this to generate essentially an x and a y grid. These are my coordinates. That's the same as the mesh grid function in MATLAB, okay? So this is essentially exactly the same as the mesh grid function, and I'm just generating an x and a y grid. And that just has, that x grid goes from minus 2.5, minus 2.4, minus 2.3, and so on, right? And it does it in 2 dimensions, the same with the y. And so I have x and y, and now I'm applying my Gaussian equation. You remember the Gaussian equation was, our Gaussian equation that we are using was e to the minus x squared minus y squared, right? And this is what I'm doing here now. Now I'm doing the NumPy exponent minus x times x minus y times x, y times y, right? Minus x squared minus y squared. And then the function is returning the x values, the y values, and the z values. So I now have an x array, a y array, which is essentially the same because they both go from minus 2.5 to 2.5, and our z array. The z array is the Gaussian hill, is the elevation of the Gaussian hill, okay? So if you can, in Spider, the nice thing is you can just select this by left mouse click and holding on it. And then with the right mouse click, I can say run selection or current line. So now I'm running this. So instead of typing it, it has been copied to this window. And now I have my Gaussian hill elevation defined. Back up a second. Everybody able to have Spider open? Everybody has that Python, the Gaussian hill Pi loaded? You're welcome to type this too. You can type it too if you want to, but I'm usually a lazy person, so I like to do copy and paste, okay? So, can you guys help if you or was there a question? So if you get stuck somewhere, there are a couple of Python experts around that can help. This is on the GitHub. If you go on GitHub and you go in the directory DEM Gaussian Hill, you would have the function GaussianHill.py. And you also have the PDF or the Python notebook, whatever you do. So for self-teaching, if you're into, or maybe after the workshop you're interested in revisiting some of those things that we have done, maybe there is someone actually interested in this. The Python notebook for that is very, very useful. Yeah, that's a great self-teaching thing. So when I did this, I actually did it last night, that notebook. I always spend extra code time to explain what is being done there. Yeah, so you should be able to follow along. So let's go one step further. And as I said before, we can take the derivative of the Gaussian, right? So So I wanted to explain the next function. Is that okay, or should we wait a little, or? Sure. If you scroll down, so if you
This number depends on the user. How many number of steps you are defining?
So n depends. So when we go from minus 2.5 to plus 2.5, so it's a length of 5. The height is 1. And if you say n is 100, then you would have 100 divided by 5. No, so 5 meters divided by 100 steps would then be the equivalent of, something 0 point or something meters per second. So I can talk about this a little bit, but n essentially allows you to get a different EM resolution.
It's not necessary to define n earlier than giving a command.
Yes, we can. Yes. So I usually like to define the function first, and then concerning Python, if you are, because we are going to plot a few things in a second, and I think Python by standard doesn't allow you to have the figures separated. If you go to Spider Tools Preferences and you hit the IPython console and you click on Graphics, make sure that you have selected as a backend automatic, okay? Because then the graphics will be not in the window down there, then you will have a separate window for the graphics, which will be very useful in a second. So again, you go to Tools, Preferences in the menu. If you go to Tools, Preferences, that window should come up. This is called Preferences. And then you click on the IPython console. In the tab Graphics, you have the option of selecting the backend. And this should be set to automatic. I think it is set to inline by standard. And so you want to change that to automatic. Yeah, it's set to inline and you want to change that to automatic. Okay? Good. Let's go to two more definitions, and then we make some plots. And the two definitions that I would like to go to, I generate two more functions. One is a slope function, and the other is a curvature function. And these are just the analytical, the first and second derivative of the Gaussian. And I'm being really lazy here, and the reason why is because I don't want to take a derivative in the x and in the y direction because that would be more complicated. So I'm saying, hey, we have a Gaussian function and the x and the y is the same, right? So it doesn't matter if I'm going in the x or in the y direction, it's all the same. So I can call this r. So I could actually rewrite my Gaussian function to be e to the minus r squared because x in that sense is the same, right? And x and y is the same. So if I then take the derivative of e to the minus r squared, the derivative is 2 times r, and then I say e to the minus r times r. Okay? So I just defined my r. I'm sorry, I did. Actually, r is x squared. R is x squared or y squared. Okay? So, and that is minus 2r. So the derivative of e to the minus r is 2r times e to the minus r, right? That's the derivative. And then if I take the derivative of the derivative, so the function is now 2rn to the 2r e to the minus r times minus r, you take a derivative of this. So you have 1 minus 2 times r times 2 e to the minus r times r. So that's 2 times the derivative. So our g 2 prime, so the derivatives, the second order derivative would be 1 minus 2 r squared times 2 times e to the minus r times r. Yeah? So this is our analytical, the first order derivative, the second order derivative, so slope, curvature in an analytical fashion. And now we ignore those 2 other definitions, yeah? And we jump down to plot analytical solution of Gaussian Hill, yeah? So let me just briefly explain what I'm plotting here. So now we have defined those functions. We have the Gaussian function, we have the first derivative and the second derivative, okay? So slope and curvature. And now we want to visualize them. Now we want to plot them so that we know what we are looking at. And the first thing we do is we define that we want to have 111 steps. So again, our grid goes from minus 2.5 to plus 2.5, and we use 111 steps. You can use any number here. But you probably don't want to use 1,000,000 because then it gets really, really slow, because then you have a grid, 1,000,000 times 1,000,000, and then it gets slower. Just let's use 100 or 111. That's a reasonable number. Then I'm generating, then I'm telling Python to prepare a plot, and I'm telling Python to prepare a subplot so that I can plot 3 different parts. And I want to have, these are my 3 different parts, 1, 2, 3, and I'm doing that by saying subplots, 1 x line, 1 y line, and 3 x lines. So 1, 3 means just 3 subplots in a row. And now I'm filling those 3 subplots with elevation, slope, and curvature, okay? So this is why I'm saying do a subplot. And then I'm calling my function Gaussian Hill elevation. And all I need to give that function is the numbers of pixels, right? Because we defined it up there to go from minus 2.5 to plus 2.5. And I'm just saying, okay, make me a Gaussian Hill with 111 points in both directions, in X and Y direction. And I get back the X, Y, Z coordinates, right? Because this is how I defined the function back there. And now I can plot the grid of Z coordinates, because that's the height. You know, it doesn't make much sense plotting the X and the Y coordinates because they go only from minus 2.5 to plus 2.5. That's not any useful. So I'm plotting the Z, the height, and I'm using the image show. IM show stands short for image show, and it shows me my grid, my Z grid. Z is an array, the Gaussian Hill array. And I'm just giving it a color map, and I just like the color map that goes from yellow to blue. And that's called the Civilus Color Map. And if I plot this, you see that you have values going from 0 to 111, 0 and 100 to 11. That's the X and Y direction, right? And my height goes from 0 to 1. So this is the Gaussian Hill. So you can envision this is a flat terrain, right? This is a flat terrain surrounding the Gaussian Hill, and then in the middle is the Gaussian Hill. It's the same into all directions, right? So this is our bulb that we have sitting here. That's our digital elevation model, okay? So that's the digital elevation model of a Gaussian Hill. And now I can take it a step further and say, okay, let's do the same for the slope. So now I plotted, now I'm plotting here the Gaussian Hill slope. And I'm plotting the Gaussian Hill slope again with 111 pixels. So this is the analytical solution. I'm not taking the slope of the DEM, I'm taking the analytical solution, okay? And the analytical solution then tells me the slope goes from 0 to 0.8, and the way it is, the way we would expect it, if you think the shape of a Gaussian Hill, if this is our Gaussian Hill, so this is what we just plotted, right? The height is 1 meter, and from here to here we have minus 2.5 to plus 2.5, right? This is our grid. So this is, if I would draw a profile through here, it would look like this, okay? This is my profile drawn through the Gaussian Hill. And now if I take the slope, I would assume low slope, high slope, low slope at a very, very simple large scale view of it. And this is exactly what we see. At the very peak, we have low slope. Then the slopes gets higher and higher. The slope is the largest here at this point. This is where the dark colors are and the blue colors. And then the slope gets slower again, and go back to 0. This is where we are back at the flat area. Okay? So this is our slope of the Gaussian Hill. Okay? And then I can do the curvature. This is the last section here. So the curvature is essentially the curvature is then the second derivative. This is the curvature. This is a curvature along the steepest slope, by the way. The curvature means that we have a curvature that is mimicking this shape, right? We have a curved shape at the top that looks like this, and then the curvature goes in the other direction at the bottom, right? So you have the curvature up here is different than the curvature down here, right? So we talk about a convex concave curvature. So we have a positive curvature here because it's bending this direction and then it's bending backwards. This is where we have a negative curvature. and then where we have zero curvature at this location, meaning that you have essentially the same slope. The slope is not changing. Curvature is the slope of the slope. So we are just looking at in what direction is the slope changing. Is the slope changing positively or negatively? And here the slope is increasing. This is why we have a positive curvature. And then down here we are at this part, right? The slope is decreasing. So that's why we have a negative curvature. This is why the colors are blue here. Okay, so always keep that. I always like to have the Gaussian hill in mind, that when I think about curvature and slope, is you always know the shape of the Gaussian hill, right? So you can say, okay, at the top of the Gaussian hill, the curvature is positive, this is this shape, and then if we go to the bottom of a Gaussian hill, it's bending in a different way. We go from steep slopes to less steep slopes. This is why we have a negative curvature there, okay? Convex, concave. Everybody with me so far? By the way, do I need this microphone? Okay. Okay. I just didn't hear it. Okay, good. Perfect. Okay, should we discuss this a little more? Does this make sense so far? I'm happy to repeat things. Yeah, okay. Okay, good. The next step would be, now that we have our Gaussian hill, we want to generate a numerical slope. So now we want to do what we do when we have a DEM and we click on the slope button. We want to calculate the numerical slope, right? So we want to fit our dx, dy direction, and we compare that to the analytical slope. So this is the perfect slope, right? We know the derivative of a Gaussian function. And now we want to compare it to our numerical slope, yeah? And we do that by just defining a slope function. So our slope function, you remember this guy that we had, right? By the way, can I make this higher? I guess not. So you remember our, this is dy, 1, 2, 3, 4, 5, this is dx. So, so how do we calculate our slope? Well, we can define our distance of y, for example. So we just want to, oops, I'm seeing this is, hold on. Okay. All set. I just unscrewed the pen. So in order to calculate slope, I need to know what is the distance between those pixels, right? And then what is the absolute elevation difference. I'm just defining, I'm just calculating the distance. D means the distance between the pixels. So I'm looking at the pixel between the first y pixel, or the second y pixel and the first y pixel, right? So I'm going from 0 to whatever the coordinate of our y pixel is at. In fact, I could do this manually. So if I'm going to call this, I can just select this and go run. And this is how, here, let me make it, oops, no. Let me make it bigger here. So given the 2.5 to 2.5 and 111 steps, we have a distance of 0.045. This is our distance that every cell is apart, right? So this is the step side. That's our grid cell resolution. Let's ignore the units for a second. This could be meters. If you say we go from minus 2.5 meters to plus 2.5 meters, we have 111 steps in it. We would have a grid cell size of 0.045 5 meters, which would be roughly 5 centimeters. So, you know, just for the sake of the argument, let's say we have roughly a 5 centimeter grid here. Yeah? And then the next thing is we're using the NumPy gradient function. The NumPy gradient functions need the height information and it needs the distance. And the NumPy gradient function does for every single pixel, it's taking the x and the y direction. So we are taking the derivative all along the x rows and all along the y rows, okay? And that goes really, really quick because that's a code written in C. And we just need to tell NumPy that we are using the distance, the step size. So NumPy needs to know the step size because the gradient depends on rise over run, right? So you need to know what is the horizontal distance. That's the cell size. And then I'm just saying, okay, what was the equation again that we have been using? We wanted to have the gradient, and I'm just saying we take the gradient of the derivative in the x direction squared times the derivative in the y direction squared. So essentially, this is the scalar product. We are generating the vector of the steepest descent. So if you think about this, now I need more space. Hold on. So so if you're thinking about your this is your grid cell size. So you have this is the grid that you're looking at. You have the derivative in the x direction, the derivative in the y direction, and you take that squared, the sum of the square root of the sums, and that essentially gives you the angle. For example, it may look like this, or the angle may be this direction. Whatever your angle is, this is essentially the slope that we just calculated. Okay, that's the magnitude of that slope. So if we go back to, so what we just did is, hold on, I'm pulling this up. I just want to make that. So what we just did is, we did this term, okay? The dx squared, dy squared, okay? And we take the square root of this. Okay, this is what we just did in the Python code. We are ignoring the arctan and this guy because arctan just turns it into radians, and this would turn it into degrees. But you know, we don't need this for the purpose of deriving the slope, right? But you could put an arctan and n pi arctan in front of it, then you would have the degree in radians. Okay, I ignore this for now. The same way, you could generate an aspect calculation by looking in the dz dy and dx dz direction, okay? But that's something we would do later. So we just did this term here, okay? So this is our slope, okay? And now we have a function that takes an x, y, z grid. So we give it the x direction, the y direction, and the z height, and we derive the slope from it. And we get the magnitude of the slope. This is the same as what is being done under the hood in GDAL or whatever you use for calculating your slopes. Maybe someone uses the GDAL DEM slope command or something. This is exactly what is in there. You know? So this is the step-by-step approach that GDAL DEM slope is using. Okay, so let's come back to maybe before we do that, I'm sorry for the confusion. I just wanted to show you something what you can do with Python, and what I'm doing here is I'm generating a 3-dimensional plot. So you can by using this axis 3D command, you can do 3D plots, and we are just making a scatter plot of x, y, and z, yeah? And we are plotting it in coordinates of 3D. And the nice thing with Python is you can now move this around. So you can now look at it from different sides. This is our Gaussian hill, okay? And I think all of us would agree that this is our Gaussian hill with the height of 1, and the x-axis and the y-axis go from minus 2.5 to 2.5. And you see the grid spacing. We have 111 points in here. You could do it with 1,000 points too. Then it would be much denser, okay? So I think we all agree on the shape of the Gaussian hill, right? We can take it a step further, and we could say, hey, let's plot our plot in 3D, but let's use the slope as a color scale. So meaning that we can plot the same Gaussian hill here, and now it's colored by slope. And it looks nicer on my screen. Somehow the projector doesn't give it across that well, but we see the low slopes here, then the slope is increasing, here it's the steepest, and here the slopes are going down again, okay? So that's this function that we looked at. So let's now come back to the comparison of the analytic and of the numeric slope. We can now plot this right next to each other, and we can here we can plot. I'm now plotting the analytic slope. What we did before, the derivative, and now I'm plotting the numeric slope. That's the gradient in the x and in the y direction. Okay, and then taking the square root of x squared plus y squared. And at first sight it looks similar, but our eyes may be deceived too, right? So the usual thing that you do is we would generate a DH surface. So a surface that looks at the differences between those two DEMs. So you can think about this as being two digital elevation models. This is one digital elevation model. Oops, this is what's not supposed to be. Something went wrong. Hold on. Here. This is one digital elevation model. This is another digital elevation model. This is our analytical slope. This is our numeric slope. And if we look at the difference, we get those very typical artifacts that are associated with the gridding artifacts. So that shape where we have higher slopes in the analytical solution and lower slopes in the analytical solution, that is the pattern that we observe. So in other words, this is the error that the numerical gridding introduces, right? We know what the slope should be based on our analytical solution. And this is the slope that we get. And if we look at the difference, we see the differences specifically in the high slope areas. You see up at the top, the slope is the same because the slope is very low slope. And then as soon as we get into the steeper slopes, the steeper the slopes, the higher, the larger the problems in that sense, okay? So this is why we get this pattern. And if you're interested in digging deeper into it a little, you can look at Taylor Smith's paper in Earth Surface Dynamics. It's on the GitHub page. There's a subdirectory called Journal PDF, and I put that paper in there. So if you're interested in exploring these issues a little more that happens when you do numerical derivatives, this is something that happens in there. Why you would want to do that? Well, let's ask the question, or let me ask it this way. How do you know you can trust your slope calculation? When you have a DEM, any DEM, maybe a 30-meter DEM, maybe a 1-meter DEM. How do you know that you can trust your slope calculation? Because you're not doing it analytically, you're doing it numerically. You know, every slope in a GIS that is being calculated is doing it numerical by looking in the X and the Y direction and taking some mixture of that. But we don't know the true slope, right? We don't know what the surface is a fractal surface. I mean, real topography is fractal, so we can't take the derivative of it. But we don't know what the true slope is. So we just take the slope for granted that we get. And the motivation behind this is that we say, well, let's see if we can take a surface where we know the analytical slope because we can take the derivative, and we compare it to the numerical approach so that we get a better understanding of what are errors that are being introduced by the numerical approach. And why do people spend time on either doing a dy dx or a plane fitting or a second order polynomial or a fourth order polynomial? Why you would want to do that? And you know, I think looking at this and seeing that there are differences makes you suggest, okay, I need to make sure that I derive my slope properly. Maybe I should say this becomes very important with lighter DEMs or high resolution DEMs. If you have a 30 or 90 meter DEM, you're not estimating the real slope anyway. It's, you know, you look at a smooth landscape anyway. But having a 1 meter DEM and you're looking at smaller scale slopes and you start to compare smaller scale slopes, you want to make sure that these are real slope changes and not some numerical artifacts that you're introducing by taking the dx and dy slope. So that's, you know, what we could also do, this is the absolute height difference. You could express it as percentage of the absolute height. In other words, this is 0.005, and this is 0.001. The height of the Gaussian hill is 1 meter, and this is 0.1% of it. You know, you have, and in fact, sometimes the slopes can be high, the uncertainties can be higher. You can have uncertainties of several percent in the slope if you don't do it right. And then it becomes important, you know, especially when you look at slope distributions over a larger landscape. You know, you're comparing 3 and 4 degree slopes, for example. Then the question is, how true are those slopes in reality? So that's part of the purpose why you would want to make sure that you understand how you derive slopes. So basically the bottom line, what I want you to take away from this is that when you calculate slopes, no matter what you do, you will have artifacts in your data. And you just need to realize what are the magnitudes of these artifacts, of these problems. And taking the slopes in curved terrain is specifically tricky for the steeper slopes. So here, where we have steeper slopes, here we have the largest discrepancies. Where we have low slopes, there is essentially no discrepancy. So that goes in the same direction when we were comparing the Tandemax and the SOTM data. You know, that's a data-based uncertainty. This is a numerical-based uncertainty that is always there. There's no way around it. You know, so that's inherent to your analysis. Again, at 30 or 90 meter spatial resolution, this doesn't matter. But if you go to meter or even sub-meter spatial resolution, this becomes really, really important. Let me ask, what's the idea for now? What we want to, you know, we could start with something where we look at distributions, or we could just tinker around with this a little more and then call it a break. I think it has been pretty dense so far, right? Should we maybe recap some of this and then we start with something new after the break? Is that, yeah? let's make sure that everybody is on the same page. Are there questions, concerns?